length of day. Is the length of day also can be determined from the variation of the gravity. So before that, I need to explain a little bit about Earth's tensor of inertia. Earth's tensor of inertia is characterizing the mass distribution inside the Earth. The mass distribution is not only the solids, it's also atmosphere, ocean, and hydrosphere. So this tensor is 3 by 3, and I will show it by I bar t. It means that it changes in time, and it has 9 elements. 1, 3, 1, 2. As you see, 9 elements. This is symmetric. So in fact, there are 6 elements that which are important. So as you see, this t equals to this one, this equals to this one, and this one. And this inertial, for example, the first moment of inertia is computed by this integral. Integral over x, y, is x and y is a coordinate system, Earth's coordinate system, y2, z2, dm. dm is the integration element. So 2, 2 will be integral over x, integral over z, x2, z2, dm. dm elements of the mass. 3, 3 will be the other one, x and y, and x2 plus y2 dm. And the other elements of the tensor of inertia are I12 is 1 integral over x, y, and dm. I13 minus y, z, dm. And I was 2, 3. I13 is 1 x, z, dm. So these are the theory about the theoretical or the formula for computing the tensor of inertia of the Earth. And this tensor can be written in terms of two other tensors. For example, this tensor, I bar t, can be written in terms of a, let me see, a, b, and c plus. We explain them what they are. C13, C12 is also symmetric. 2, 3, C 1, 3, C 2, 3, and C3. This term is a constant term, or constant tensor, and it's called variable or variations. So, what is the connection between this tensor and the gravity? That's the important question. It is known and it is proven by a guy with Chen. It's a big formula, 2005, that the C20 spherical harmonics of the gravitational potential is 1 plus chi prime 2. Chi is a love number. 2m r2 integral over the whole area 2 z2 minus x2 minus y2, this is 2, and dm. So Now, that's interesting. We see something here which is very similar to the formula, integral formula for the tensor of inertia. Then let us write this the following way. I write this integral is this form. This integral, if I consider minus then z minus z, I can add this. I can write this 2z. I can divide it by 2. Then it will be divided by 2. Let me see. I divide it by 2, and then I see. But then I can write this in this form. C20 will be 1 plus the second log number, 1 over 2, the mass of the Earth, the radius of the Earth square, and it will be minus I3 plus I I22 minus I33. So if we simplify this, it will be 1K2 1 over MR2 multiplied by IYY I22 average divided by 2. So the interesting part here is that the second order spherical harmonic coefficient of the Earth can be written in terms of inertial tensor, inertial elements of the or diagonal elements of the inertial tensor. That's interesting. So if I want to compute the third one, this element I33, I can simply write it I33, and it is changing in time. Then I say, okay, it's function of time, and solve this I33 from this equation. Then I can simply write I22, the average of the moment of inertia, and equatorial actually, minus MR2 C20 1 plus K2. So this is the moment of inertia, and this is, you see that T20 is a second degree harmonic of the gravitational potential, has the direct relation with I33, which is the third moment of inertia around the z-axis, or the third axis. So if we define trace of I, trace of the I, trace of, I say trace of I bar t will be summation of the diagonal elements, if you remember linear algebra. So I can simply write this in terms of the trace. So how I can, for example, add and remove restore and subtract from to this equation. After this remove and restore, I can simply write that the third moment of inertia is 1 over 3 trace of the tensor of inertia, or inertial tensor, or T, minus 2 over 3 MR2 C23 1 plus K2. So AC3 is the moment of inertia. And if you remember from the beginning of this for the discussion, I wrote that the moment of inertia is composed to two tensors, or the tensor of inertia is composed into two tensors. Let me write it again so you see what I mean. So tensor, let me write it the full tensor for you so you understand what I mean. 1 1 1 2 1 3 1 2 2 1 2 3 and I 3 3. So these are symmetric. Is A, B, and C a diagonal matrix plus C11, C12, C13, C22, C23, and C33. So I want to say that this I33 that I have here, which is related to this one, is simply the constant term. If I want to check the if I want to get the variation of the third, then it's simply I can write I33 minus C. It goes to the other side. The variation, this term is constant. If I want to get the variation, this is enough that it goes to the other side. So by subtracting this from that, I can say that the variations C33 will be variations. Let me trace first. Trace the trace of the variation of the trace. I would say variation of the trace minus 2 over 3 R2 variation of the second degree spherical harmonics in K2. So we could find this variation in the third moment of inertia. Why it is a third moment of inertia? Third moment is a somehow rotation around the third axis, or the S rotation axis. If this S rotation axis changes, the length of the change. Lombeck as of 1988 said that the length of the day, or changes in the length of the day in time, over the mean length of the day, which is seconds, is equal to M3. And what is this M3? M3 has a relation with this so which is equal to 1 over Cm minus omega. I will explain it. H3T plus, I write it here, rest plus omega C33. Oh, that's interesting. Length of day is related to this 3, and omega is the Earth's rotation rate, and the Cm is the principal inertia of third principal inertia of the Earth's mantle. So if I simplify this a little bit further, I will come to this equation. Length of day T divided by load mean 1 plus K2 C33 Cm Cm omega. So as you see, the trace is gone because it is assumed, it has been proved that this trace is very small. The trace, like the variation of the trace and is almost zero, and it comes based on this assumption. So in that case, if you have this sigma 33, which from the gravity or changes of the second degree harmonic, and you compute the WC is the moment of the inertia or angular momentum of the Earth, and you have this moment of inertia of the mantle, speed of rotation of the Earth or its rotation, then you can compute the length of day. This is the log number, so it's 31. So that's all. The ratio of this, the length of day to the mean, which we already have, 86,400 seconds, can be determined like that. 2/3 cm m, mass of the Earth, radius of the Earth, changes of the second degree harmonic in time, plus third angular momentum of the Earth, Cm and omega. So if you want to determine, you want to know what is this values. Cm is 7.044 37 kilogram m2. Omega is 7 minus 5 radian per second. So m is the mass of the Earth, which is about 5.97, 36, 24 kilogram, and r is the radius. And K2 here is minus 30, minus 10. So based on this, you can simply determine the length of day. So from the gravity, you will get this term is constant. These are, you can compute as well. These are from the inertial tensor of the moment of inertia multiplied by the speed of the Earth, and this term is constant. You multiply this one to the right, and you can get the length of the variations. Length of the variations from the gravity. But one thing that you need to consider is that this gravitational potential of the Earth is the result of different perturbing accelerations or perturbing phenomena. Therefore, you have to somehow consider this is the change. If this is the change due to the gravity, the changes of the gravity, you need to consider the solid type, atmospheric pressure, and ocean tide. You have to compute these effects, and you know how to compute these things, and you have already discussed about that, and remove them from the determined CO2 coefficient. Then what you get is actually residual, is the corrected one. Then you will come to length of day, or variation of the length of day. So in it is also considered that atmospheric pressure should be added back because it is some part of this Earth system, atmospheric. atmospheric pressure. Atmosphere is always around the Earth, but solid tide is the things that which comes and go. So they are periodic variations. So this is permanent. So it is written in the article that I'm talking about that the atmospheric pressure should be added back. So what you get from Grace data actually is already corrected for the solid tide, ocean tide, and these things. But when you want to use them, you should read about the atmospheric pressure. When you have the time series for this delta C20, compute the effect of solid tide and ocean tide, remove them from them. Or if you have a gravity field, some of them, the gravity fields are corrected for these things. So they should be corrected for. Otherwise, you have to correct it yourself. Then you will come to this residual. This residual, or I would say that not residual, I would say that the delta C20 is corrected for the solid tide, ocean tide, atmosphere. And this is what you need to use for determining the variation of length of day based on the formula that I present. But you need to consider that the variation of the trace of the tensor of inertia is 0, which is not far from reality, and with good approximation it is correct.